Okay, what I'm going to do now is give you a quick review of forces as vectors. That will help you solve some of the problems with friction. But just to go back over some of the things we've already learnt, when you represent a force as a vector, and that allows you to analyse it graphically, and also you can do analytical solutions from that too. A force that could be represented as a vector would be a line, which would represent the line of action over that force. The length of the line would represent the magnitude of the force, and in this case we could go in one of two directions, so we need to indicate the sense, and that would give the indication of which way the force was acting. And this might be say a 5 Newton force represented by that line in that scale. Now what we could do also is we could realise that that particular force could be part of a whole force system, or it could itself be a resultant of a whole force system. And if it was a resultant, there might be several forces that all finish up creating that single force, which we would call the resultant. Now, the other thing about that is that sometimes it's better to analyse forces in easy ways when we're doing the math on it. For example, if we can break an angled force, say the force was on an angle, like turn it around so it's tilted, so that it's actually not running to the horizontal, it's on an angle to the horizontal, then we could resolve that force into its components horizontally and vertically, and that might make mathematical treatment easier. So that force there would be resolved into, and I might just do this in a different colour so that you can see that they're different forces. So you've got one force acting down, which would be the vertical component of that force, so that force vertically. And then there's another part of the force which is acting across, and that would be the horizontal component of that force. So that 5 Newton force can be resolved, and you'd use your parallelogram method there. That would be that you would extend the line across so you can see where it came from. I actually have done it rather ordinarily, but that would create a parallelogram where these two sides make up the parallelogram as well. So there you've got your force resolved. And that would be to whatever the angle here might have been. It doesn't really matter what the angle is at this point. If you were doing it analytically, not graphically, that particular angle is important because then these represent certain angles. And that one over here, because if that's the internal angle in here, that would actually be the opposite. So that would be opposite onto the hypotenuse. So that would be sine of the angle. And this one here, which is now the adjacent to the angle on the hypotenuse, would of course be the cos to that angle. Now these basic concepts like that, they're going to come up over and over again. So we really do have to have our head around being able to break a single force into two component forces, horizontal and vertical, and go the other way. So if we were given the two vertical and horizontal components, we could make a resultant out of it. So just recall all of that. A force can be represented as a line, represented by a size on the line, a scale. That scale then can be used to calculate the sizes of the other parts if you wanted to work graphically. Okay, now, in the questions you've got in front of you for the friction issues, here I'll just grab the first one that we look at there, question 1. The friction issue was about the fact that we tested for, and I'll just quickly remind you of what we've tested for. We've tested the grippiness or slipperiness, whichever one you want to look at, they're the opposites of each other obviously, of a load on a slope, and we'd raise the slope up until we got to an angle, and that angle was the point at which this particular thing slid down the slope. Now there are a couple of conditions taking place there. What we recognized was that this thing has a mass, and that mass is acting vertically because gravity acts towards the center of the earth, so it's vertical, and then it's leaning against the slope, but the slope can only react vertical to itself or perpendicular to itself. So no matter where this slope is, the material in the slope is reacting vertically to it. Perpendicular is a better word actually, not vertically, because that confuses the issue. So that's at right angles to that surface, and we refer to that as the normal. The force going down the slope is a component of the weight force, and that would then be, we've seen this so many times now, we just call it straight out mg sine of the angle, theta, sine theta, mg sine theta. So whatever m is here, and whatever we decide on gravity as being 9.8 or 10, that will then make that a really easy calculation. And what that represents is the limit of friction. Now up until that point, the friction is holding it there. When it gets to that point, it slides. Now how fast it slides will depend on how much extra load or force we give down the slope. But if that's the force at that point, That's called the frictional limit. Now, we use mu as the symbol, and we might come up with an angle, and that angle can be returned into a tan, rise over run, and that would be the tan of the angle. And that can be given a representation of some sort of size, and maybe this particular ratio turns out to be 0.3. That would therefore be the coefficient of friction for that particular surface, whether it be wood on wood or brick on wood or whatever it might be. And we can keep tabulating those things until we have a whole list of them. And that particular number is going to apply whether it's on a slope like that, or it's on a slope like that, or it's dead flat. I'm still going to have to provide a force to the normal. So the next part of this is that the friction force at the limit is equal to, the friction force on the normal is equal to 0.3. And that particular relationship will come up again too. So now you've got two important things to recall. A force can be divided into its horizontal and vertical components, and that friction opposes motion, but it's easy to calculate what it was. And once you've got a figure for it, you can apply that figure to any situation in which you find two forces or two pieces of material against each other. So back to the question we have in front of us. What this one's asking us to do is very simply calculate what the force is that I need to push on this particular package. It's a 12 kilogram parcel to continue sliding at uniform velocity. Now the reason it says uniform velocity is I don't want it to accelerate. So all I want to do is get it going and keep it going. And what it's telling me there is the kinetic friction, which is a slightly smaller number, because when it starts moving, it's not as hard to move any further. There's a couple of reasons for that we talked about in the previous lectures. So this one is 0.25 and it's kinetic. So that's while it's moving, all I need to do is supply a 0.25 ratio between the force and the normal. So that's going to be easy to work out. Nice simple problem to get us kicked off with. So we've got that one there ready to go. I'll put that up there where I can see it so I can work to it. And there we go. If I do this just as a sketch, removing that material, so making a free body diagram out of it, I now have a situation where I've got a force which is going to be the one that I've got as friction, so that's going to be friction, and because it's moving, we'll put a little K underneath it for kinetic. And then there's the normal, which is going to be the reaction force at the surface due to the mass of the object coming down. So let's put that in a different color to just make sure we can separate the two. And that, of course, is mg. Now there's no sine theta attached here because it's horizontal, all right? So I've got to push with that force to keep it moving, because there's a force actually acting the other force. The friction force is really going the other way, and I'm supplying a force that's equal to it to keep it moving. But I will get that from the formula that I just showed you a moment ago. That is that the frictional force, in this case kinetic, is equal to 0.25. And that's also equal to the force that I need to overcome, K, on the normal. So those two things are equivalent. Right, if that's the case, we can do a quick calculation where I put in what I know is the normal. Normal is mg. So in this case, what was the load? 12. And 12 times 9.8, but I'm going to do it as 10 for the easy one. All right, so that makes it nice and simple, 120. And that's in newtons now, because it's a force, because I multiplied kilograms by a acceleration. Now, that comes over into this part of the formula, and I'm looking to find out what F is, so I want to rearrange the formula. So I'll finish up with F as K equals 0.25, or a quarter of 120. So times 120, because that's our newtons over here. And a quarter of 120 is, of course, everybody, 30. Good. All right. So that means that I need to apply a load of 30. Now, notice here he's got 29.4, or rather the answer on the sheet here is 29.4. Clearly, that's because I used 10. And because I've used 10, I can keep the maths nice and easy. That's only because in exams 10 is quick and easy to work with, and it's okay. But if you did it the right way and made that 9.8, or rather the right way, a alternative way, 9.8, you'd have a different number for the force, and therefore you'd finish up with what he has, 29.4. So that's nice and simple, okay? Now, a little bit more difficulty when you start to introduce little red herrings, or not really, they're things that are adding to the process. So I'm jumping now to question 10, because The ones between 1 and 10 tend to be just examples of the same situation, relatively simple, where the friction and the normal are pretty much straightforward. Now this one though, this is a slightly different situation. What we have here is a chest on the table, or on a mat that's got it down here, on a floor rather. And then it's asking you firstly to determine which one will slip first, and that's not too difficult to work out. So we've got a 45 kilogram chest of drawers. The chest is placed on a mat and pushed as shown. Given that the friction, in this one S, static, that's the friction while it's sitting still, is 0.55 for the chest and drawers, and remember that the limit of friction and the static friction values are the same generally. There's no reason to suspect they're not going to be any different. So the limit of friction, the point at which it just starts to move, is the same as the static friction. And the mat for this one here, the mat and the floor, is 0.35. Now we've learnt from what we saw earlier that the lower the angle, the easier it is to slip. The lower the angle, the lower the ratio. So the coefficient of friction with the material with the lowest coefficient of friction is going to be the slipperier one, so 0.35. 0.55 will still slip if you get there, but you'd have to make sure that the floor isn't moving as well, so the mat must crumple up or something, but that's just complicating the issue. So the answer to the first part is really simple, the one with the lower coefficient of friction. Now, having determined that that's where it's going to slide first, in other words, the chest is going to stick to the mat, but the mat isn't going to stick to the floor, we now have to work out what is the force I need, this one, to get it to move. But there's an issue. If I push down, when I'm pushing down onto the top of the cabinet, I'm actually increasing the load of the cabinet, because part of what I'm doing is pushing down. Just to represent that, we'll draw a little diagram again. Useful to keep going in graphical form, because the graphical form shows that up better. So my friction force, or rather my supplied force, the force that I'm going to be pushing with, has a component running down. And that component is going to add to the weight, mg, of the chest of drawers. So those two are going to add together, and that's going to create a bigger normal, because the normal now will have to be equal to the mg, or the mass times gravity, of the chest of drawers, plus this component of F that I've created. And what is the component of F? Well, back to that first drawing we did, where you break things down into horizontal and vertical components, and because it's a simple one that we've always come across, and you'll always see these over and over again, where the angle is provided to the angle at the horizontal. So this one's straightforward. It's going to be that F, and its sine, again, of 40 degrees. So down here, what I'm adding to this is F sine 40. Okay? So just keep that in mind for a moment. Oh, and this one here, this is the actual force I've got available to push horizontally, because the friction is resisting in that direction. That's the friction of static friction there. And I'm going to provide a force to overcome that, to move that. So this and this have to be the same, and that one is F cos theta, 40 degrees here. I said theta again because it's there. All right. Now that's the condition. So I've analysed the problem and got myself to a place where I can look at it from a couple of vectors. So let's try and do that. Oh, pretty colours. Move that out of the road, get to a fresh sheet underneath. Okay, now that we've got that sorted out in our heads and we have an idea of what all things are, we can start working on them as an analytical solution. First thing we had was that U, S, which is the same as the limit of friction in this case, is equal to 0.35. We've also worked out that because of that, we know that the friction at the limit point on the normal is equal to that. We want to find what that friction is, what we have to provide rather to overcome that, and we got that from looking at our component of this force, so that component of that force, which was F and cos 40 degrees. That therefore equals FL. And the normal, we just said, was now an additional force, which because we've added gravity to it, and we've got mass times gravity plus the force component down the slope, which was F sine of 40 degrees. So from those pieces of information, we can start to put together a formula that will help us solve and resolve down for the force F. the original force, the force that we're pushing into, on an angle, the top of the cabinet. And the way we finish up with that is we look at it like by solving, basically just solving what we know against each other until we get a result. So, okay, having sketched all that out, now we can start an analytical solution. And what we know from our sketch is that we're provided with the coefficient of friction at the limit at 0.35. The coefficient of friction is equal to the friction at the limit on the normal, and that's where that ratio came from. We've also worked out that because we're providing a force F on an angle, the component that is acting horizontally, which opposes or overcomes the friction, is the same as F cos 40 for the original F. And that, because we do it with the calculator, and I've rounded it up a little bit to save our numbers, 0.766 F, and you can check that by putting that through your own calculator. The normal now is going to be the addition of mass times gravity and the component of the force F, the one we're trying to find, acting vertically down. So those two get added together, and that's 441 for that. I'm using 9.8 this time, so we're more closer to the answer in the book, or the ones I've given you as an example. And that's multiplied by 0.643, again, finding that from the calculator. So now what we do, and I'm going to walk you through this because I noticed in class that some of the students there had a little bit of difficulty with just the manipulation of the maths. It's not that terribly difficult. So if we go back to this formula here, so that's our condition, and these are the pieces of information. So if we put those in, so if we've got 0.35 is equal to, in this case we're going to put in FL, which is 0.66 F, and that's all on top of the normal. And this time the normal is 441 plus 0.643 F. Now we've got to do some math to get rid of that and get F to be the subject somewhere in the equation. So we'll take the bottom half first and multiply that across. So 0.35 times all of that from the base underneath of it plus 0.643 F. All right, that's then going to equal our 0.766 F. You've got that so far. Now by multiplying out, 0.35 of 441, 0.35 of that one there, we finish up with, I think that's 154. I'm just looking over at my notes, 154, 35, because I'm not doing this in my head, I'm not that good. And 0.35 of 0.64 is plus 0.22. Make it 225 F, because we can, it's not rounding up one way or the other, so 225 F. And that is all going to equal 0.676 F. Right, now what we've got is that I need to get rid of the F part here, so I'm going to minus it from both sides. So I get 154 will equal 7.66 or 0.766 F minus 0.225 F. And that comes to, looking across, 0.5. 0.5 for 1 F. So that's just taking those two out and making a single figure out of it. So now I've got about half of F is equal to that, really what's that saying. Now if I want to find out what F is, I simply have to divide both sides out to get rid of the 0.5. So divide this side by 0.54, divide this side by 0.54. So I've got 1, 5, 4, 3, 5 divided by 0.541, and that's going to equal the value of F. Now note, that is the F we started with. We want it. That's because we've resolved it in components, but now we've got to find what would be the value of the original F if I'm going to finish up making this work. So that's straightforward. That comes out to, lo and behold, 2.853 newtons. And if I think yes, that's what we were supposed to find. So that's good. That's quite straightforward. The big deal here was to remember that we have added forces to the normal, and we just resolve it for the F we wanted to find in the first place. All right, now, last one of the problems I want to show you today anyway is one of these ones, the ones with the ladder. Now, these are actually quite good to do graphically, not analytically. And there's a reason for that, is that the information here provided, often in the exams, will be provided in a way that's to a scale you can actually apply with. I think I've got one or two here that are about the same size as what we need. So I'll just grab those. Here we go. I've enlarged them up so you can see the scale. So if we just look at that from the perspective of that might be an exam question, and usually about that same size. Now there's a couple of really interesting or important things to remember here. In the question, it talks about a smooth, uniform, a ladder of uniform size, or we'll talk about what that means, on a vertical or smooth vertical surface. Two of those things are important: uniform ladder, smooth surface. When it's a uniform ladder, that means that every element of the ladder is the same mass all the way along, which means I can concentrate the mass, or put the mass acting as a center of mass, so concentrate it all towards the middle. So find the middle of the ladder, and I'm not going to try and measure that out. I can probably, what is it, looking at the runs, it's probably right there. Acting straight down. So the total mass, and in this case, what was it? It's 18.37. So again, we got mass times gravity. So we can have 18.37 kilograms times 10 or 9.8, doesn't really matter. Because we're going to do it graphically, when the error creeps in with graphical solutions is such, we'll make it 10 to make it nice and easy. So we've got 183. I don't need a calculator then to work out what that is. So that's 183 newtons are acting straight down. Now, what that'll also do is that means that we can now see that there is a difference between where the things are leaning, and it's not straightforward. We're not actually able to cancel things out straight away. That doesn't seem to be touching the ground. So where is our normal? And where is our stuff? Where are all the friction's coming? It's telling us that this is a smooth surface here. So that means that there is no vertical resistance taking place at the wall. The ladder can't do anything there. There's no interpenetration. That's not a real situation. That's not what the real world's like. But for this problem, that's what you're told. So we have to agree with that. That wall is not frictional, or there's no friction there. So in that case, the only way the wall can react is out at a normal to the wall. In this case, right angle. Still called a normal because it's a right angle. And that's one of the things you have to remember. As a normal to whatever the angle of the surface is the right angle to it. We'll still have a normal down here too. So we're still going to have a reaction to the load at the bottom where it's actually touching the ground. So what we have here is a force at the wall. And over here we've got the normal to the load coming down. So that's going to be so that's the normal to the surface of that. So that's equal to 183.7. Why? It's the only vertical place. Right? There's no vertical reaction here. There's nowhere else. It's not touching the ground anywhere. This is the only place that it can react to that load. And for equilibrium, given that we remember that we learnt that we have to have all of the forces valued in an equilibrium, so forces vertical have to equal 0. The sum of the forces horizontally have to equal 0. And in the condition that we've learnt recently is the sum of the moments also has to equal 0. And those are the things needed to make that ladder stay where it is. All right, so now we've got a couple of things happening. Where is the friction taking place? Well, if the ladder was sitting on the wall and they were both smooth and that was smooth and this was smooth, the ladder wouldn't stay there. It'd just slide and fall down under its own mass. So the friction force must be opposing motion in that direction. Okay? So if that's the case, then we're probably trying to overcome the load that this is creating by pushing out that way. Otherwise, where's the capacity to stay there coming from? So there's a force acting across here. And those forces cancel each other out. So that solves the condition there. This guy here and this guy here must be the same. That's where that force is coming from. The only horizontal forces are those two, and so therefore that's cancelled out. We've already decided that works because we've got rid of those two. All right? So now we've got a situation. I'll go to another sheet because I'll come back to the moment problem in a moment, because that sorry about that. What we'll need to do now is recognise that the three forces that are taking place, I'm going to grab a pencil for this, all right, they have lines of action. There are three forces involved. What three forces? Well, we've got the force that we talked about just then, opposing the motion of slide, that's our friction. We have the force due to the normal at the ground there. Actually, I've drawn that a bit too far over, but it will be in that point there. And I'll come back to that in a second. So that will be our normal force. We've got our load running down, which we know, and our one at the wall. All right. Now, those two can be resolved into a single force, which at this stage we don't know where it is. But we've got an idea it's going to be acting like that, right? And that's the reaction force to the ladder. So the ladder is actually providing a force going the opposite way to which the normal and the friction are responding. Together they make up that one force. Bear that in mind, keep that in mind for the moment. That is a resolution of two forces into a single force. We just don't know where it goes yet. We don't know its angle. But we can work it out, because if they are in equilibrium and you've got 1, 2, 3 forces, anytime you have 3 forces in equilibrium, they are concurrent forces. That means they pass through one point. So remember weeks ago when I raved on about 3-force equilibrium systems, all forces concurrent? This is why. Now you can extend the line of action out of the wall, extend the line of action that we know straight up and down. Now I haven't done this very accurately here because I'm just doing it rapidly to show you the principle, although that wasn't too bad. Those two meet here. But what about our third force? Our third force has to meet there as well if it's in equilibrium. 3 forces in equilibrium pass through the one point. They're concurrent. But the only thing we do know is that it also passes through that point. I've drawn that badly, but it's right there. So where the ladder is touching the ground and where this guy crosses is the line of action of our third force. Now, what is the third force? I can actually use the diagram here to work that out. A bit hard to see with the pencil, but I've actually drawn a triangle. So what I've got is my force going down, that's the load, mg, and I've got my force at the wall, which is also the friction force, because by the fact that we looked at here, the horizontal forces have to balance out. So that force and that force equal each other. So that's our friction force across there. But it's the force at the wall. And then you've got the reaction force going back up, cancelling it all out. So those two forces combined finish up creating a reaction force that removes the load and stops the whole thing from falling over. So that's our triangular forces here for equilibrium. So that means that if I was to work out a scale for here, just measure that. Now in this case on the diagram here, straight off the diagram you can see that's about 10.5. So my scale here would be 10.5, in this case centimetres, is equal to my original load, which was 183.7. Alright, so I would divide that through, put just to what my scale is. So what is 1 centimetre equal to? Well, 1 centimetre will be 183.7 divided by 10.5. Now I haven't got the calculator with me at the moment to do that, but looking at that, you can see it's going to be that 1 centimetre is approximately going to be equal to easily 118 newtons, by just looking at how that's going to work out. So that's on this scale, on this drawing. Now everybody's drawing could be different, depending upon how it was enlarged, but because I can take it straight off the scale, then I can do this. I can go over here and read my other scale. So this time it's looks like 1.4 there. So now I've got 1.4 times 18 will give me the friction force. Again, I'm not sure what that's going to be. What's 1.8? So it's going to be like 20, what, 23, 22, 23. You guys can do that with a calculator. And coming down here, we've got a load, or the reaction is about 10.8, something like that. So it would be 10.8 times 18, and that would come back to something in the order of about 190 something, 192 by the looks of that, or maybe just 190. Now I'm guessing those two numbers just to give you a rough idea. The thing is that I've calculated those simply by doing a graphical solution on the diagram. That makes that a really easy question to solve quickly in an exam. How would you do it analytically? If you had to do it analytically, what would the issues be? Well, it's not that much different, because what you remember now is that we've got those 3 conditions again. So go back to our 3 conditions. The sum of the forces that are vertical will equal 0. The sum of the forces that are horizontal also equals 0. And lastly, the most important one for this particular one, the sum of the forces that are moment forces also equals 0. So any turning forces have to be 0. We can see from what we've already done, we know the friction force and the wall force cancel each other out. So we've got the horizontals nailed. We know that the vertical force coming down here, which is the mass times gravity of the ladder, is being resisted by the normal, which is acting up there. So the normal and mg sine theta, or mg, no sine theta going on here, mg is going to be the same, so that one's cancelled. But what about the turning effect? What is happening is that the ladder wants to try to slide down and move, and it wants to rotate about any point in space there. If I held it somewhere, it's going to spin about it, because the forces are at angles, or at distances rather. Then, so they're going to, a force times a distance creates a turning effect. But if I hold it at the base, down here, I say, right, I'm going to hold the point there. What I've done is there are no distances now to the normal or the friction force. Those forces pass through that point. If they pass through the point, they do not create a turning effect about the point. That's a very important thing to remember. You have to have a distance to the force to get a moment. So right away, what I've done is I've cancelled out my concern with those two things. They pass through the point, they don't create a turning effect. But the thing's in equilibrium. It's not falling down, it's not spinning. So that means that this guy, which is trying to create a turning effect around that way, holding the point here, the ladder wants to turn around and go around that corner, is being held up or resisted by the wall, providing a turning effect in the opposite direction. So now we've got two forces combating each other to cancel out the turning effect, the moments. So that's what we do analytically. So we can take that now and we go, what is the distance to the first force? We worked out from the previous one that what we said we're going to use 10, so that's 183.7 newtons. And it's at a distance of half of 2 meters. Why half? Because it's in the middle of the triangle. Right? If it's in the middle of the hypotenuse, it's in the middle of the triangle. So that's halving that, because they become two similar triangles. So the sum of the moments, let's say we make that positive, so this first one's going to be positive, is equal to 0, and it's now equal to 1, the first force, 183.7 times 1. Pretty straightforward. What about the other guy? The other guy isn't at 7, because his line of action comes out there. His line of action for distance at right angle is that distance there. But that is not hard to calculate, because what that will be is, looking at the angles here, we've got 2 on 7. So if we've got 2 on 7 for the hypotenuse length, we could calculate that height using Pythagoras, because we're already given it. You could also work out the angle using those two things and go to a sine relationship if you like. How would I work out that? Using Pythagoras relationship. Okay, quick piece of paper here in front. Grab a blank piece. Well, there's so many pieces written on now. All right, come back here. Okay, just because you might have a bit confused about the maths. We've got a hypotenuse, so we'd have 7 squared. That's not very good. 7 squared, and that's the hypotenuse, is going to equal the other two sides, or 2 squared, plus whatever d is, d squared. Right, now that's what we're trying to find. So you just resolve that around 7 squared, 49, 4 plus d squared. Take d squared out of there, so therefore d is going to equal the square root of 49 plus 4, and I again need a calculator to work that one out, so the square root of 53, and that would be d. So if I keep it in that third form just for the moment, you can then see that if I go back to this one, we're going to minus, because it's going the other direction, we're going to minus the distance, the root of 53, times what the frictional force was up here, which is what we're going to find out, because that's what we don't know. So the force of the wall, so times force of the wall. What will allow me to do then is I can rearrange that to force in the wall is going to be equal to 183.7 divided by the root of 53, because I've divided both sides by that And that will come out to an answer which is the same as what I would have found from the other one, using the scale. I'm going to leave you to do that because that's not too terribly difficult to follow from there. A lot of stuff on the page, but and you resolve that to a rational number rather than leaving it in a surd form, of course. But it's simply the idea that we're looking at moments now. And once we get that solved, we've determined the components of the force backwards. We know now what the value of the wall force is, which means we know the value of that force. We know what normal is because it's the same as that. So once we find those two, we've got that value and that one, we can go back and create triangle of forces to get the resultant. The resultant will come from knowing what that value is here, that F, and the normal, and the resultant. So you work backwards. It's not too hard to do. All right? Have a go at them. Talk to me at classes or send me an email if you're still having trouble with it, and I can try and do a better job of explaining that. Look at that. It's all over the place. Anyway, that'll do for today. You should have a go at them. There's a couple like that. There's another one here with extra force. The only thing about this one, what was it? No, I can't see what the difference is. Graphically determine. Oh, so it's asking you to graphically determine it. So here it wants you to do it analytically. This one's just saying do it graphically, which is that solution I've got in front of you. Okay, happy solving problems. See you guys in class.